Hello, my name is Zarkhan, and this is my third lab experiment on the black hole in Physics 2211. And so here's an introduction, some key ideas and vocabulary. So there's going to be two computational parts in this lab experiment. The first one is going to be finding the mass of the black hole, and the second one is going to be finding the trajectory to escape the black hole. And so here's just some vocabulary that's going to be important to us. So of course we're going to be using Newton's second law, which is basically just says that an object's acceleration is dependent on net force being applied to the object as well as the mass of the object, and then velocity, which is just a function of speed with meters per second as the units, and then gravitational force, which in this case is going to be like the black hole, the force of the black hole to the ship or the planet. And so the objective of this experiment is obviously to find the mass of the black hole as well as the resultant velocity needed to escape the black hole with the ship. And so in the first part of the experiment, the system is going to be a black hole, and then the surroundings is going to be the star. And then the second is going to be systems is the spaceship, and the surroundings is going to be the planet and the black hole. And so in the first part of the experiment, we're going to be really utilizing these component equations, calculating parallel and perpendicular components, and then resulting in F net. And then in part two especially, we're going to be using these three gravitational equations, and it's going to help us calculate both the mass of the black hole and the resultant velocity needed to escape the black hole with the ship. And so here are the initial conditions in part one. As you can see, G is just the gravitational constant, which is 6.7 times 10 to the negative 11. The mass of the star, delta T, which is converted like 1 day into seconds, 86,400, and then T is left at 0. And then this is the actual code itself. As you can see, we're using initial and final velocities for calculating momentum and F net. And then we're using the equations I showed before in the previous slides to calculate parallel and F net parallel and F net perpendicular. And then we're using all of this information and plugging it into the gravitational equation to find the mass of the black hole. And here's just the end of that code. So this is the result of our first computational model, our part one, and we see that we get the result that the mass of the black hole is 1.45862 times 10 to the 34. Okay, so moving on to part two, these are the initial conditions. The mass of the black hole, we just calculated that in part one. G, the gravitational constant, remains the same, 6.7 times 10 to the negative 11. Mass of the planet, ship, and delta T is 0. Delta T is 1, and T is 0. And yeah, these are just the initial conditions. And here's the actual code. Here we're just using a repetition of the universal gravitational equation. So we're calculating R and R hat, and then just plugging it into the gravitational equation. And then here we are using the velocity and position update formula to actually make the planet and spaceship like move in the code. And so here's a result of this code. So we see that the ship is now 1.17683 times 10 to the 11 meters away from the event horizon of the black hole. And so here's the planet's orbital speed. The planet's orbital period is about 2 hours. And there is error in my code since the trajectory is pointing upwards. It's actually just supposed to curve. So yeah, there's definitely some error in my code. Okay, so what does it mean and what if? So in your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So basically, I don't think there's any difference because they're both equal to one another. I guess just the main difference would be that the rate of change of momentum, but that could be calculated before part one without the mass of the black hole. And then what if, instead of wanting to take a quick look at the black hole and leave, you decide you want to enter into an orbit around the black hole? What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Your spaceship should still not crash into the black hole, nor crash into the planet. I think that the ship's speed must be equal or like greater than the planet's orbital speed um, in order to enter the black hole, but I'm not really sure. Okay, thank you.